Hi, everybody. This is Lights, Camera, Build, building audio and video with Bazel. So on a normal day, Bazel builds software. And it builds it fast and correctly, and it aggressively caches its outputs to avoid rebuilding. But you all know that pitch already. So how does it do that? Bazel rules define actions on inputs and produce outputs. And under the hood, inside these rules, you have actions. And a rule will invoke something like ctxactions.run to call usually a compiler or any tool that's taking in inputs and transforming them into outputs. And so typically, in the simplest case, you've got code coming in. A compiler is processing that and outputting an executable binary. But what if we wanted to build audio files instead? So I've been, as a little side project for fun, working on a still unfinished Bazel rule set called rules multimedia that aims to do just this. But in order to build audio, we'd need an audio compiler that would play an equivalent role. And there's a great tool for that called SOX, which stands for Sound Exchange, the Swiss Army knife of audio manipulation. It's an open source tool that takes in audio, processes it, and outputs more audio, and can apply effects in the process. And so there's a huge variety of effects that you can apply. You can add delay, you can add reverb, you can automatically trim silence, you can also deliberately trim a certain amount of silence off the beginning and you can shift the pitch, you can shift the speed, you can shift the tempo, you can add reverb, repeat, dither. Dither should cause a little bit of worry. If you know about audio processing, what that's doing is it's mixing random signal into the audio file, which obviously is non-deterministic by default, which would break caching and wouldn't be particularly nice for a Bazel rule. Thankfully, there is a -R flag on SOX that sets a random seed. You can also turn off dither, and so through either one of these methods, you can eliminate that that source of indeterminate results and end up with something reproducible. And so beyond that, SOX is actually a suite of tools. So there's SOX itself, which manipulates audio files, and SOXy, which shows metadata about audio files, Rec, which records audio, and Play, that plays audio. And so for now, I've put together a tool chain for all of the multimedia tools that I'm using, and I'm just pulling them in through rules nix packages right now. Maybe at some point I'll try and find a way that doesn't require dependency on nix, but for my purposes right now, it means I've got a hermetic tool chain. Now, the fact that SOX takes in audio and outputs audio has some implications for Bazel rules. Typically, in a normal rule set, we'll see patterns like mylang library and mylang binary that will each take sources and depths, because you can build up a dependency graph of libraries that are each outputting intermediate compilation steps. And keeping track of them in providers, and you need to keep track of all of the transitive dependencies of your libraries until you can finally feed them into a binary. And so you're bringing in each of these targets, or in each of these rules, in the targets you're defining with them, you are having to identify source files and also dependencies that are typically pre-built. Since our SOX audio rule is just audio all the way down, we just have sources, which can also include other SOX audio targets. And each audio file is fully self-contained, so we don't need to track depths. So the typical starting point is to get some audio together. And so you can invoke rec like this with Bazel if you want to, but you can just put audio files into a repository, into your Git repository, or use Git LFS if the files get too big. But you just want to get them into your Bazel workspace. And then you can start defining audio targets and that take those audio files and apply effects on them. And so here is, we take our piano file that we recorded and define a new target that takes that as a source and applies an effect to slow it down. And we're calling that slow. We can also define targets that take in multiple audio files and combine them in particular ways, adding effects in the process. But we can also define how we combine them. So by default, SOCKS will just concatenate the files one after the other, or the audio and the files, into a single audio file. But we can also mix that audio together. So we can mix it into multiple channels. We can merge it into one channel. And one cool thing that we're doing here also is that we can make the SOCKS audio rule executable. And so you can Bazel run that audio, and it will play it on the command line. And we do that just by, after doing the initial context actions.run to build the audio file, we can also write out a script that just calls play on the resulting output. We can also use the SOCKSy tool, which outputs metadata, as something to build automated testing on. And so when we run SOCKSy on an audio file, it will output a bunch of metadata that might be useful for us to check. And so the number of channels, the sample rate, the precision, the duration. And then we can write SOCKS tests that assert that metadata is accurate. The same, and we're not talking too much about video today, but you can do the same thing with video using Ffmpeg, which is a very powerful tool for manipulating both audio and video. And so there's some overlap, and we can do things that SOCKS can't do, and we can also do some of the same things with video. And there are analogous tools to Play and SOCKSy, ffplay and ffprobe, to respectively play audio and video and print media file metadata. And so what we have here is, what we end up with is declarative audio and video editing. We can structure a graph of audio and video manipulations. Since SOCKS, when we set the right flags, is reproducible, we can cache intermediate steps and only recompute things when the underlying audio files or the targets have changed. And we can play back intermediate targets, and as well as the final results. And we can test that output media conforms to specifications. Can it compete with professional audio and video editing software? Of course not. But you can do cool things with it. And I think it's being able to structure a graph of audio manipulations is a fun approach that I don't know if it has been tried too much. And so last night in my hotel room, I decided it would be fun to make something really silly just to show this off. And so I just recorded myself saying BazelCon and then thumping myself on the chest to get the bass drum sound. I processed each of those components. And then SOCKS can also output, without any inputs, it can also, like, it has a built-in synth. And so you can synthesize audio. So I synthesized this weird synth sound from that. And then in the end, I combine it all, mix it together into a single audio file, and repeat it. Oh yes, and previously I'd repeated the bass drum, so we get the kind of like 4 on the floor type thing. And we can see if we can play it. So this is just kind of a starting point. There are some other ideas that I want to incorporate into this. One is an aspect that can traverse your build graph and synthesize audio based on the shape of your build graph. And so I started to work on this. It works, but it sounds bad right now. I would like it to be something that both is somewhat informative, and you can actually hear the shape of your build graph and also sounds nice. I told a coworker today about this, and he said that most build graphs I imagine sounding like this, and I said that's pretty much how my aspect sounds at the moment. And there are some other things that I'm trying to add on. I want to be able to output waveforms in the command line or like when you add an output group, and so you can see the waveform of the audio in the process. So there are all sorts of little things, but I'm making progress, and I want to try and make some more meaningful audio, experimental music, something with this. And so we'll see where that leads. Thanks a lot.